Okay, any questions? Any questions about anything before we start? Just want to remind you that a week from tomorrow in this room we have a prelim during class. And before that I'm going to post last year's prelim 2. And then a little later I'll post the answers to last year's prelim 2. And in the meantime, there's 2 homework sets out. One of them is nominally due today. That's homework 8. Or last week. 9 is nominally due today. Or no, Thursday, sorry, okay. Yeah, 9 is nominally due Thursday, 8 is nominally due today. Or no, last Tuesday. And so what I'm going to do is I'm going to issue a final deadline for 8 and a final deadline for 9. And I'm leaning toward like having the solutions for 8 go up sometime Saturday. So you take your risk. As long as what?
As long as it's not tomorrow. Yeah, tomorrow is probably tomorrow.
Okay, no, it's due at 2:54 p.m. tomorrow. No, okay. Just kidding. And 9 is going to be, the solutions are going to go up Monday sometime. So maybe Monday noon. I might just pin it down because I want you to have them before the test. Okay? So just be forewarned that emails are going to be coming out about that. And now I'm really worried because I haven't seen Manish in like 3 classes. Balaj, can you tell me what's going on with Manish?
He was in our last class.
He was in your last class and he's not here? Well. Yeah, okay, and that's probably where Ju-Sung Kim is because he's all 3100. Oh, okay. Yeah, and some wacko pre-med orgo course on Thursday probably. Yeah, anyway. Okay. All right, so no question. Yeah, Alex. There's no official makeup time, but if someone has some conflict, or I know there's one person who's going out of town for an athletic trip, and I've made arrangements with that person, and if you have a problem, just email me and I could probably make an arrangement for you individually if it's a compelling reason. Okay, last call for questions before we start. All right. Well, we started talking about these endpoint signals, and we're leading up to the DFT and the FFT. And as I said before, these are the things that are actually going on in computers when you do signal processing. So it's good to understand what's happening under the hood. And we define the following. We say that X in C to the Z, so we're talking about discrete time signals with complex values, is an endpoint signal when X of n is 0 for n less than 0 and for n bigger than or equal to capital N. So an endpoint signal is just one that starts no earlier than time 0 and ends no later than time n minus 1. Okay? And I didn't tell you this notation last time, but I decided I'm going to go with it. I've been rewriting the DFT and FFT chapter, and I think it's going to be a lot cleaner and prettier to look at, fewer subscripts and all that, and also slightly different order for some of the things. And I'm using this notation. S sub n is going to be the set of all endpoint signals. It makes the definitions easier and stuff. Instead of saying for every endpoint signal x, we can say for every x in Sn. And at the beginning of this, remember I told you that throughout this whole discussion, you're going to be wondering how much of this is really about signals and how much is just plain linear algebra. Because really it is just plain linear algebra. And on the other hand, it's about signals. That's why we're interested in it. So I'm going to try to sort of develop those 2 parallel universes simultaneously. And the first piece of that is that Sn is a subspace of C to the Z. And it's pretty clear that it has dimension n. And every x in Sn can be mapped to a vector that I'm going to use x underlined for in C capital N. X vector is just going to be the vector whose entries are the possibly non-zero values in the endpoint signal x. And unfortunately, a lot of the, everything we talk about matrices and vectors, we have components 1 through n, and signals are 0 through n minus 1, so there's going to be a lot of p minus 1s and q minus 1s floating around, and I'll try to keep that straight for you. And the vector operations on Sn map nicely to the vector operations on Cn. In other words, if I take a linear combo of two signals in Sn, that signal maps to the same linear combination of the two vectors, the vector associated with each signal. Furthermore, Sn is contained in L2. And I forget actually whether I talked about this last time. Remember what L2 is? L2 is the set of all square summable signals. And it's also an inner product space. And therefore, Sn, quote unquote, inherits, that's a typical math term, the L2 inner product. And what is the L2 inner product? So for x and y in Sn, inner product of x and y is going to be the sum from n equals minus infinity to infinity of x of n complex conjugate of y of n. And because x and y are endpoint signals, this sum actually only runs from 0 to n minus 1. So that's the inner product on the set of all endpoint signals. It's just the same old inner product on L2, but restricted to the set of endpoint signals Sn. And lo and behold, that inner product, as we would hope and perhaps expect, maps under the signal to vector correspondence to the standard inner product on Cn. And that's important to recognize. So observe that this inner product maps to the standard Cn inner product. So over here in Sn, you have inner product of x with y. This is in Sn, set of all endpoint signals. And that's the sum from n equals 0 to n minus 1, x of n, y conjugate of n. And that's vector y associated with the signal y Hermitian transposed times vector x. And this is what's happening over in Cn. So again, we've got this parallel universe of linear algebra, and on the one hand, you're talking about vectors in Cn and things you can do with them. On the other hand, you're talking about signals in Sn and what you can do with them. And last time we talked about the cyclic shift. If you're given an x in Sn and an n0 with n0 lying between 0 and n minus 1, and you actually don't need that, but I'm going to assume that, C shift sub n0 of x is the endpoint signal with specification C shift n0 of x at time n is x of n minus n0 mod cap n for n between 0 and n minus 1. And just to make sure you're on the same page, what is the value of C shift n0 of x for n less than 0? C shift sub n0 of x is an endpoint signal. It's 0. What is the value of C shift sub n0 of x for n bigger than or equal to cap n? 0. Endpoint signals are 0 before time 0 and 0 from time n onward, and often I will just specify what they're doing between 0 and n minus 1. Actually, this 0 less than or equal to n less than n. Between 0 and n minus 1, because that's the only places where they might possibly be non-zero. Okay, now I showed you what cyclic shifting looks like. It's a video game kind of thing. You move all the values to the right, and the ones that slop off the right-hand end, you paste them back on at the beginning in the same order that they appeared before. How do we implement this linear algebraically in the parallel CN universe? So, in terms of signal vectors, and this is another thing what we actually did last time, and sorry to repeat, I'm repeating a little more than usual today on purpose. Partly because it was a real skeleton crowd on Thursday. Not that, well, today's a little better, definitely. In terms of signal vectors, what happens? In Sn, you have C shift n0 of x. And over here in Cn, you have what I call a matrix C subscript n to the n0 times signal vector x. What is this capital C matrix sub n? And what does to the n0 mean? So Cn is a matrix. It's the n by n matrix specified by the following formula. And I didn't give you this formula last time. I just drew you an example of what it looked like. The PQ entry of Cn is equal to 1 when P minus Q mod n equals 1 and 0 otherwise. And what this Cn looks like, it has 1s just below the diagonal all the way down, and then a 1 up in the upper right-hand corner. Cn by itself, multiplying signal vector x, implements the shift by 1. Cn to the n0, multiplying signal vector x, implements n0 shifts by 1, and those sum up to the n0 shift. So Cn, quote unquote, implements shift sub 1, C shift sub 1, and Cn to the n0 implements C shift sub n0. Okay, so yet another thing. Something's happening to signals, something else is happening to vectors, and that's going to pervade this whole discussion. Okay, so that's pretty much where we're at from last time, plus a few additional things like this SN notation. Another operation you can perform on endpoint signals is circular convolution. And it goes like this. Suppose we have two endpoint signals, H and X. And I'm choosing those letters purposely to be suggestive of what's going to happen. Suppose H and X are in Sn. The endpoint circular convolution of H and X, and again you can use prepositions there. You can say circular convolution of H with X if you want, doesn't matter, is the endpoint signal. And you know, I thought long and hard about coming up with a pretty notation for this, like a star with a circle around it and underneath it, all that kind of thing, and I failed miserably, so I'm going to give you a really awkward notation. Cconv sub n of Hx. And I see a lot of scowls out there. With specification, C con sub n of hx at time little n equals, see if anybody can guess what it's going to be. Erica.
Would you, I guess, multiply x at times the shift, like h shifted up? So, okay, h of x, and then you basically do that, but then this extra part here would bring.
Yes, exactly. That's what you do. Okay. Now what I want is a clean formula for that. You have it. You have exactly what you have to do. Okay. Let's go with Will first.
Okay. I guess we're going to have
Some. You're going to say okay.
and then we'll figure out the bounds later, I guess.
This is good. This is good.
H of k, I guess we'll use.
Let's use m. Little m.
Oh, m. Okay, sounds good.
Yeah.
And then x of mod base mod n of n minus n.
Exactly. Now the limits.
I guess we just do n 0 to n.
0 to n minus 1. Very good. So he just described the equation doing exactly what you described in words. Okay? So what this looks like, and this is for n between 0 and n minus 1 inclusive, and what are its values for n less than 0, little n less than 0? 0. What are its values for n, little n bigger than or equal to capital N? 0, yes, because it's an endpoint signal. This looks just like the formula for convolution, except when we had an n minus m in x, we have an n minus m mod n. Okay, that's really cool. So that's a circular convolution. And as you might imagine, based on your vast knowledge of convolution, developed over the course of this semester, and the 2200 semester, you took 2200, whatever that was. The first thing we want to mention about convolution is that it doesn't matter where you put the m, and it doesn't matter where you put the n minus m mod n. So here's a fact. You can put the n minus m mod n in h and the m in x. That is to say, C conv sub n of h with x at time n equals the sum from m equals 0 to n minus 1 of h of n minus m mod n times x of n, for 0 less than equal to n less than capital N as well. And sometimes it's convenient to be able to do that. So that's a property we noted right away about convolution, both in continuous and discrete time. It also holds for this circular convolution, this endpoint circular convolution. And proving this is really easy. You just have to expand out what that is and get rid of the mods. And that proof is in the monograph. And all those proofs, the proofs of these things, they all hinge on expanding the sum out and getting rid of the mods, as I said a minute ago. And so it hinges on this kind of a thing. That if I have x of n minus m mod n, that's equal to x of n minus m when m is between 0 and n inclusive, and it's equal to x of n minus m plus cap n when m is bigger than little n and less than cap n. And what you do is you take that sum and you split it into two pieces to get rid of the mods using this formula, and then you play around with indices of summation, and voila, you have that at the end. Okay. And I don't want to go through these arguments in class because they're not really helpful, in my opinion, to understanding the material. All right, so that's circular convolution. Now, that's in signal land. What's happening in linear algebra country? What's happening over in CN? This, I bet you wouldn't be able to guess unless you do it ahead of time. Clearly, if you're given H, and you let X run over all the set of endpoint signals, conv of H with X is a linear operation on X, right? If I take two X's and linearly combine them, then I get the same linear combo of convs of H with linear combinations. So it ought to be implementable, so to speak, in Cn using matrices of some kind. Just like cyclic shifting, being a linear operation on endpoint signals, was implementable using matrices. So let's see what's going on over in Cn. So what's happening in Cn to the signal vectors? That is to say, what is the signal vector for conv of Hx, which is conv Hx underlined in terms of the signal vectors for H and the signal vector for X. Okay, this is kind of interesting. Well, it turns out if you set matrix H equal to the following matrix, and I'm going to do this for n equals 4, just for the heck of it. H of 0, H of 1, H of 2, H of 3. And this is for n equals 4 only. And I'll show you how to generalize it. And the second column is going to be the cyclic shift of this column down by 1. So you're going to start off with an H of 3, and then you're going to have H of 0, 1, and 2. And then cyclic shift again. Start off with H of 2. And finally, you start off with H of 1. Is that right? And in general, for general n, the hth column of H equals cyclic shift of H by Q minus 1 signal vector. So the zeroth column, the first column of H is the cyclic shift by 0 of signal vector of H, the signal vector for that, which is just the signal vector for H. The second column is the cyclic shift by 1 signal vector of H, and so on down the line. And that's what's true for general n. It turns out if you set H equal to that, then the signal vector for conv sub n of H with X equals matrix H times signal vector for X. It's David.
There's a Q that looks a lot like a 7.
A Q that looks a lot like a 7.
That C shape.
Yeah, okay. I'll Qify it. There. Okay. So that's how the cyclic or circular endpoint circular convolution gets implemented in terms of linear algebra. And by this commutativity property, by the fact that you can put the x with the m and the h with the n minus m, you could also make a matrix out of x and a vector out of h and do the same thing, and they would come out the same. But yeah, no problem.
What was the significance of the underline again?
Okay, underline a small letter or underline a signal means the vector corresponding to that signal. Okay, let me emphasize that. If I have something underlined, and this is a signal, by a signal like c shift sub q minus 1 of h, that's a signal. And I underline that, that's the vector in Cn associated with that signal. And let me just make the signal tilde tilde signal. Okay? So if it's a little x, it's the vector with x of 0 through x minus 1. If it's a little y, it's a vector. It's h, it's that.
So that only works for like some point signals.
It only works for endpoint signals. We're sitting in the world of endpoint signals here. And capital N is fixed throughout this discussion for now. Yeah. Yeah. Okay. Someone else had a quizzical look over here, I forget. Not you guys, no. No, you're too. you're just like the Marines or something, right? No. Okay, so anyway, you can implement this thing using matrices and vectors, and that's a good thing. That's a good thing to know. So now you can sort of see why MATLAB is so good at this kind of stuff, because MATLAB is great at manipulating vectors and matrices, and all these signal operations are things you can do by multiplying matrices by vectors or doing something to vectors, whatever. Okay, so that's the circular convolution. All right, so anyway, moving right along. Now we know all about endpoint signals and all about what you can do with them. Now we can define the endpoint DFT of an endpoint signal x. Okay, so given an endpoint signal x, so given x in Sn, that's the set of all endpoint signals. Because x has finite duration, it certainly has a DTFT. So since x has finite duration, x has a discrete time Fourier transform, DTFT, x hat, and equation DTFT, the forward equation for the discrete time Fourier transform, holds because it's a finite sum. And by this I mean that x hat of little omega equals, the definition of the endpoint, or the DTFT is n equals minus infinity to infinity, x of n, e to the minus j n little omega, but that sum runs only from 0 through n minus 1 because x is an endpoint signal. And that's true for all omega. All right, so every endpoint signal has a DTFT. And it's given by this formula here. Now what I want to do is I want to, quote unquote, sample that DTFT at n, capital N, equally spaced frequency points. So consider sampling. And I'll put sampling in quotes because that's something we think of usually in terms of signals. X hat at the capital N equally spaced omega values k2 pi over n for k running from 0 through n minus 1. So k equals 0, I'm sampling at omega equals 0. K equals 1, I'm sampling at omega equals 2 pi over n, and so on. When you do that, you get n numbers, capital N numbers. So you get capital N numbers x hat sub k for 0 less than or equal to k less than n, given by x hat sub k equals x hat of k2 pi over n. 0 less than or equal to k less than n. Simple enough. The n tuple of numbers you get by doing that So here's the definition. The n tuple x hat sub 0, x hat sub 1 up through x hat sub n minus 1 is called the endpoint DFT of the endpoint signal x. I better not underline x because then it looks like a vector, right? So that's it. That's what the endpoint DFT is. It's just you take the DTFT of the signal x and you sample it at n equally spaced omega values, those particular ones, and you get n capital N numbers, and those capital N numbers, that n tuple is called the endpoint DFT of x. Okay. So that's what it is. Now, clearly, we defined it using signals and stuff, but we can go over to the parallel universe of linear algebra and see that really it's just something linear algebraic to do with a signal vector of x. And to that end, what I want to do is take a closer look at that equation that gives us x hat sub k. Okay, so here's some notation. And this notation is non-standard, but I think it's better than the notation that they use in books. Like in books, they use capital W for what I'm going to call psi sub n. Now, this psi is different from the psi's in wavelets. And I don't think there'll be any confusion because you know, it's going to have a subscript always along with it. So given n, capital N, set psi sub n equal to e to the j2 pi over n. That notation we're going to hold on to throughout this discussion. That's what books use capital W for. This is what's called a primitive capital Nth root of unity. Why? Because if you raise psi sub n to the nth power, what do you get? You get e to the j2 pi, which is 1. Right? And in fact, if you raise psi sub n to any integer multiple of capital N, you get 1. So more generally, psi sub capital N to the L times capital N equals 1 for all integers L, positive or negative, or 0. Was that my phone? No, I don't think so. Could have been. Why do we introduce this notation? Well, it turns out that we can re-examine this equation here. So look again at the equation for x hat sub k. What is x hat sub k equal to? X hat sub k equals dt of t x hat evaluated to k 2 pi over n. And from the equation for x hat of omega, for all omega up there, that's the same as the sum from n equals 0 to cap n minus 1 of x of n e to the minus j n k 2 pi over n. And this is for all k between 0 and n minus 1. But what's this term here? We can psiify this term. What is this term here in terms of psi sub capital N? Anybody? And if Ian has the answer, I'll call on him this time because I called on Will before. This is the sum from n equals 0 to cap n minus 1 of x of little n times what? If psi sub n is e to the j2 pi over n, what's that term there in terms of psi sub n? Alex. Psi sub n to the negative k, you say? Well, where does the little n come in? Yeah. Psi sub n to the minus little n k for all k's. So we can express the DTFT values as a sum like that. Now let's form a matrix. Let's form a matrix. Capital psi sub n so define the n by n matrix. Capital psi underline sub n as follows. The PQ entry of that matrix is going to equal little psi sub n to the negative p minus 1 q minus 1. So for example, for n equals 4, psi sub n looks like this. Matrix psi sub n looks like this. It has 1s across the top. Got to leave myself some room here. So I'm going to put it on the next board. So for n equals 4, we have psi sub 4 equals this matrix. It's going to have 1s, like so. And it's going to have psi sub 4 to the minus 2 here. Psi sub 4 to the minus what? 2 times, no. Psi sub 4 to the minus 1, psi sub 4 to the minus 2, psi sub 4 to the minus 3, and it turns out symmetric. And this is going to be psi sub 4 to the minus 4. And the last one's going to be psi sub 4 to the minus 9. So it's a big matrix full of powers of little psi. And you can imagine it's pretty easy to generate this in MATLAB, right? If you take a matrix full of size, just size, and you pointwise power it to the matrix that has the right powers, then you get that. That's one way of doing it. But anyway, psi sub 4 equals that. So that's what psi sub n is. If you set that matrix psi sub n by that definition, then you can implement this DTFT equation as follows. First, define vector x hat to be x hat sub 0, x hat sub 1, up through x hat sub n minus 1. So it's the vector whose entries are the DFT values for x. Then what turns out to be true is vector x hat, and I could put it here, but I'm not going to because I want to emphasize it, so I want it to have a center stage position on some board rather than a kind of afterthought kind of position. Whoops. Then, drum roll please, vector x hat, thank you, equals matrix psi sub n times signal vector x. Okay, so that's what's going on over in linear algebra land, when over in signal land you're taking DTFTs, sampling them, getting a bunch of numbers. Over in signal vector land you're taking signal vectors and just multiplying by a matrix and getting another vector. So some people say taking the endpoint DFT of a vector is just multiplying that vector by psi n. They don't even think of it as having anything to do with signals, right? But we got at it approaching it from signals. So let me just summarize this last bit. Over in signal land, I wonder if signal land is capitalized. It's two words for sure. Anyway, over in signal land you have x hat sub k equals the sum from n equals 0 to n minus 1 of x of n, psi sub cap n to the minus nk for all k. And these have the interpretation of the DTFT of x evaluated at k 2 pi over capital N for all k. And over in Cn, you have vector x hat equals matrix psi sub n times signal vector x. So we could have gone through this whole discussion just talking about doing stuff to vectors, cyclically shifting vectors, circularly convolving vectors, multiplying vectors by this strange matrix psi n, without ever referring to them as vectors that come from signals. Okay, so again, how much is about signals, how much is about linear algebra? Open question. All right, so that's the definition of the endpoint DFT of an endpoint signal, and that's the way to look at it linear algebraically if you want. As you can imagine, the endpoint DFT is going to have some operational rules and all that kind of thing associated with it. But before I do that, before I do those, and I've been debating in my head this whole time, ever since 2:56 by that clock, whether to do this first or whether to do the inner product thing first. So let's take the 3-minute break and I'll debate it some more and then decide. Anyway, we have this endpoint DFT of an endpoint signal. We have a vector matrix representation of it, that kind of thing. Here's a question. thinking of this relationship here as a relationship between two n-dimensional vectors, signal vector x and the vector of its DTFT numbers x hat. The matrix psi sub n mediates that relationship. Question: is psi n invertible? In other words, does x hat determine x uniquely, just as x determines x hat uniquely by this equation? How many people think, without doing any calculations or anything, yes? Okay, so you're just being positive, right? How many people think no? Not necessarily. Depends. Okay, let's see. It turns out that the matrix psi sub n is invertible. And in fact, its inverse has a particularly simple form. The inverse of psi n is equal to 1 over capital N times the complex conjugate of psi sub n. That is to say, psi sub n inverse is the matrix whose PQ entry equals psi sub n to the positive p minus 1 q minus 1 with a 1 over capital N in front of it. So all you do to get psi n inverse is, and remember, the psi sub n, the complex conjugate of psi sub n to any power is psi sub n to minus that power, which is why all it does is it reverses the signs and all those things up there. How does this come about? Well, I'm just going to plug it in and show you that it works. So, and the reason I'm going through this argument is that it's the kind of thing that pops up again and again and again. So it's something you want to have facility with. So to see this, how does it go? What I'm going to do is I'm going to take the matrix that has that as its PQ entry and multiply it by psi sub n. So I have a formula for the PQ entry of that. So for the given psi n inverse, let's check that if I take psi n inverse and I multiply it by psi n, I get the n by n identity matrix, which I'm going to call I sub n with an underline. Now you see why you needed to take linear algebra before you took this class, right? Because we're doing all this matrix stuff all of a sudden. By the way, here's a like off the record, like in the math courses at Cornell, is a lot of the homework just busy work, or is it meaningful? Do you have to do some things again and again and again and again, the same exact calculation, or not terribly? Yeah, okay, good. Well, as long as there's some ambivalence about that. Because I remember someone telling me, well, I have to copy the answers off the internet because it's just busy work and I have all this other work to do. And I know how to do the problems. And I'm like, I'm not really sure. So, just asking you that. I'm thinking of establishing a website called Course Villain that has like false solutions to all my homeworks. And do some kind of search engine optimization to have it be the first hit for anybody typing in anything vaguely resembling ECE 3250 homework solutions or anything like that. What do you think? Yeah, yeah. Because they would think of the villainy as being, a student purloining these answers and putting them up online, right? They wouldn't think of the villainy as the professor trying to trick them into, putting down wrong answers. Because professors aren't villainous. Okay, if I take a matrix, the matrix psi n inverse as written above, times the matrix psi n, and I calculate the PQ entry of that, what's that going to be? That's going to be the sum from little r equals 1 to n of the PR entry of psi n inverse, which is 1 over cap n, little psi n to the p minus 1 r minus 1, times the RQ entry of psi n, which is psi n to the minus r minus 1 q minus 1. And that's the same. I can factor the 1 over n out of the whole sum. I get the sum from little r equals 1 to n of psi sub n to the r minus 1 times p minus q. And this is true for all p and q between 1 and n. And you'll notice that I will frequently, throughout this discussion, I'll write down a 0 and then have to erase it and put a 1. Or write down a 1 and have to erase it and put a 0. Because in matrices, the columns run from 1 to n, and signal space and all that, everything runs from 0 to n minus 1. Okay, what if p equals q in this equation here? Then all the terms in the sum are 1s. There's n of them. Divide by n, I get 1. So when p equals q, you get 1. So this is equal to 1 when p equals q. And when p is not equal to q, the thing there is a partial geometric series. Okay? And it comes out to be 1 over n times a fraction 1 minus psi sub n to the capital N times p minus q divided by 1 minus psi sub n to the planal p minus q. And I claim that's true by the partial geometric series. All you have to do, you change the index of summation so it goes from 0 to n minus 1, and then you let the gamma, that I always use gamma for that in the partial geometric series, be psi n to the p minus q, and that's what you get. What's that lower term equal to? What's that whole fraction equal to when p is not equal to q? Stephen?
0.
Why?
Because psi n to the n times the integer is 1.
Yes. Yes. So this is 0. It's equal to 1 when p equals q. And it's equal to 0 when p is not equal to q, because psi sub n to the capital N times p minus q equals 1. All right, so bottom line is the PQ entry of the thing we thought was psi n inverse times psi n is 1 when p equals q, 0 when p is not equal to q. That's the same thing as saying that the matrix product is the identity matrix, because the PQ entry is 1 only when p and q are equal. So it has 1s on the diagonal, 0s else. So that proves that psi n is invertible. So the bottom line is that psi n inverse candidate we had times psi n equals n by an identity. Check. Okay. So sine is invertible. Now, why do we even bother figuring that out? Because I asked you that question. Does the DFT, the endpoint DFT of the endpoint signal x determine x uniquely, just as the signal x determines the endpoint DFT uniquely? The answer is yes. Now we know that's true. So consequence, x hat vector determines x vector uniquely by means of x vector equals psi n inverse x hat vector, which is the same as 1 over cap n psi n matrix conjugate times x hat vector. And this is linear algebra speak, whatever. In terms of signals, x hat sub 0, x hat sub 1, those values of the endpoint DFT up through n minus 1 determine signal x uniquely by means of, and what we're going to do is we're going to write out this vector matrix equation in terms of signal values, component by component. X of little n equals 1 over cap n, sum from k equals 0 to n minus 1 of x hat sub k, psi sub n to the positive nk for 0 less than or equal to n less than n. And what are the values of x of n for little n less than 0? Remember, x of n is an endpoint signal. 0. Thank you. What are the values of little x of n for n bigger than or equal to capital N? 0. So we don't even have to specify them. We just specify what it's doing for 0 less than or equal to n less than n. All right? Okay, so what is cool about this? This may not seem particularly, cool to you or profound or anything, but this leads us to something that I like to think of as kind of like reverse sampling theorem. So let's see how this works. Okay, so this gives us a sort of quote-unquote reverse sampling theorem. And what I'm going to do is I'm going to, remember how we had versions 1 and 2 of the Shannon-Nyquist sampling theorem? Version 1, version 2. I'm going to merge versions 1 and 2 of this reverse sampling theorem together into one theorem. How does it go? So, what is a reverse sampling theorem? It says the following. It says that the DTFT of an endpoint signal so let's say the DTFT x hat of an endpoint signal x is determined completely by its values at the n equally spaced frequency points k2 pi over n. 0 less than or equal to k less than n. That's version 1. Alternatively, and this is going to be version 2, for any capital N complex numbers, column C0, C1, C2, and so on, up through C sub n minus 1, there's a unique endpoint signal, little x, whose DTFT x hat satisfies x hat of k 2 pi over n equals ck for 0 less than k less than capital N. Okay, so what's going on here? Let me see if I can. There's a lot of DFT versus DTFT, all that kind of stuff, and the letters sound similar, so over the phone it's hard. If you're doing this class that way, it'd be difficult to communicate all these ideas. But here's the point. The idea here is that the values of x hat at those capital N frequency points, k 2 pi over n, those are the things we called x hat sub k, determine the signal x in Sn uniquely by means of that equation up there that gives you x of n values in terms of the x hat sub k values. And in turn, the signal x determines the DTFT x hat for all omega by equation DTFT. Namely, x hat of omega equals the sum over n x of n e to the minus j n omega for all omega. And that sum runs only from 0 through n minus 1 because x is an endpoint signal. So if someone comes up to you on the street and says, hey, and this is something, this is not necessarily a whole plaza thing. This might happen, this is more of a, you know, Thurston Avenue near the multicultural thing behind Carol Tatcon, you know, that area. It's where you're likely to run into someone who asks you the following question. Says, hey, I have this, I want to figure out this function of little omega for all omega. And I only know the following two things about it. Okay? Thing number one is, it's the DTFT of an endpoint signal. Thing number two is, these are its values at 0, 2 pi over n, 3 pi or 4 pi over n, and so on, up through capital N minus 1 pi over n. I only know those n numbers, those n values of it. Can you tell me what the whole function of omega, little omega is? And you say, yeah, I can. What I do is, I figure out the endpoint signal. You've told me it's the DTFT of an endpoint signal using that equation up there. And then I plug that signal into the equation that gives me x hat of little omega for all omega, and boom, I have the function. Okay, so this is like a reverse sampling theorem because now we're talking about a function of omega that's determined completely by a discrete set of values rather than a function of t that's determined completely by a discrete set of values. And the band-limited thing for the sampling theorem, that maps to endpoint signalness in the reverse sampling theorem. All right. So anyway, that's a nice little observation. And why is the alternatively thing true? You could sort of see what's going on there. All you do is you take those C's, you pin down x hat of k 2 pi over n to be those, you plug that into the equation that gives you an endpoint signal that has that, and voila, you're there. Okay, so anyway, the one-to-one relationship between signals and their DFTs gives you this reverse sampling pattern. All right, so that's enough of the generalities. Now, well, there's one other thing I want to mention, and that is you can actually think of the DFT as coming from doing an orthogonal expansion. So one more thing before we move on. So one other item. You can view the DFT in terms of orthogonal expansions. And again, I'm going to give you a signals universe way of thinking of this, and also a CN linear algebra way of thinking of it. Okay, so first, in terms of signals, so in signal land, we've already noted that S sub capital N is an inner product space, right? And with respect to that inner product, there are many different orthonormal bases for S sub n. So note that S sub capital N has many orthonormal bases. And remember, this is, we're talking about a finite dimensional vector space here, finite dimensional inner product space. So orthonormal basis is exactly the same as complete orthonormal set. You know, we're not even have to worry about the countably infinite thing anymore because we're all finite dimensional here. So Sn has many orthonormal bases. What's a really easy orthonormal basis for S sub n? Remember, S sub n is the set of all endpoint signals. Okay, let's let n equal 4. Can anybody tell me what a pretty obvious orthonormal basis for S4 is? 1, 0, 0, 0, 0, 1, 0, 0. Yeah, yeah. And you can express that in signal language as follows. So here's 1. Signal delta. Okay, that's 1, 0, 0, 0, 0, right? Shift sub 1 of delta. Shift sub 2 of delta. Up through shift sub n minus 1 of delta. That's an orthonormal basis for the set of all endpoint signals. Now, in terms of the signal vector correspondence, this maps straight over to Cn's standard basis, the standard basis that has 1 in the jth position and 0 in the others, or ith position, or whatever. We're talking complex, so we have to be careful using i's and j's. But this maps under the quote-unquote signal vector correspondence. To the usual, the standard basis for Cn of elementary unit vectors, or whatever you called them when you learned about that. Okay, so that's one orthonormal basis for Sn. Here's another one. So another ortho basis for Sn is the set of signals that I'm going to call W0, W1, W2 up through W sub cap n minus 1. And this is where I like to use W, unlike the way that other people like to use W in this context, which is for psi, where for each k WK is the signal, the endpoint signal, with specification WK of n is equal to 1 over square root of capital N psi sub n to the nk. And that's for 0 less than or equal to n less than capital N. I'm going to put the word for in there because I've been using it. All right, now, first off, what is the value of WK of little n for little n less than 0? Zero. Yes, thank you. What is its value for little n bigger than or equal to capital N? 0. It's an endpoint signal, okay? And I'm never going to say it's 0 for n less than 0 or 0 for n bigger than or equal to capital N. I'm just going to say what it is for 0 up through n minus 1. Okay. Second of all, we better check and make sure that, first of all, these W's are actually orthonormal, in which case it follows immediately that they form an orthonormal basis because the dimension of Sn is capital N. And orthonormal vectors are linearly independent. Before we move on. So why are these W's orthonormal? And that I will pick up next time because we don't have time left today.